Now we're going to talk about how to model motion, how to describe it mathematically. Now, motion can be very, very complicated. So to start off with, we want to make as simple a picture as possible. And one way to do that is through the use of a motion diagram. So the first thing we need to do when making a motion diagram, let's say I want to model the motion of this person walking through the park. To make a motion diagram, the first thing we want to do is simplify as much as possible. So I don't want to pay attention to how the person's arms are moving or how their knees are moving. I just want to pay attention to where they are at different times. So we're going to even make a more simplified picture. This is going to be our motion diagram. We're going to start just by making whatever object I'm interested in this case the person, we're just going to make that a dot to keep things very simple. The next thing we'll want to do is define certain quantities. To start off with, we're going to define an origin. So to measure where my person is, to describe where that person is, I have to define some origin, some place that I'm not measuring relative to. In this case, I conveniently have a tree. That's very nice. We're just going to say, this is the origin that I'm going to be measuring relative to. So my person is here. It's to the left. My person is to the left of the tree. Now, we also need to define some measuring stick. Usually we do that in terms of meters. So let's say we go back. Let's say that's 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. And I can go on the other side too. And furthermore, I have to define which direction is positive and which is negative. Now this is somewhat arbitrary. I could say to the left is positive or to the right is positive. I could say to the left is negative, the right is negative. Usually by convention, you say things to the right of the origin are positive. So I would say this is 1 meter away, this is plus 2 meters away, this is plus 3 meters away. Whereas this would be negative 1 meter away, negative 2 meters away, negative 3 meters away, etc., etc. Again, it's completely arbitrary, but we do want to define our, both our origin and our coordinate system in order to accurately measure and define where my object is at any given time. One of the main physical quantities we're going to be concerned with when describing motion is the position. So position is just where I am at any given time. Now at the moment, we can see my person's position is negative 3 meters away from the origin. So we can describe our position at different times. We can do that a couple of different ways. One way is just through the motion diagram. So we could say my position at time 0. So when I start measuring, so this would be t equals 0 seconds. When I start measuring, I am at x equals negative 3 meters. Now, we can go further than that. We can say, rather than just doing a motion diagram, we can also make a plot, a graph of that motion. So I can plot my position, x in meters, as a function of time in seconds. And my initial position is negative 3 meters, so I would have to go down. So at time 0, I would be at this point on the graph. I would be at negative 3 meters. All my person did was just stay at negative 3 meters, just sat there not moving, life would be pretty boring. So we actually want to describe motion. How is this person moving? To do that, we want to know how fast they're moving. We can describe the motion using a quantity called velocity. So let's say initially at time 0, my person is at negative 3 meters, negative 3 meters away from the tree. But then, give myself a little more room here. Then they start walking towards the tree. So at t equals 1 second, they're 2 meters away from the tree. T equals 2 seconds. They're only 1 meter away from the tree. 3 seconds. They're right next to the tree. At 4 seconds, they've passed the tree by 1 meter. Okay? So this is the way my motion diagram works. We're just moving our person and keeping track of when they're at each position, what position they're at different times. I can do the same thing on my graph here. If I go 1, 2, 3, 4 seconds, we can plot our position as a function of time. So at 1 second, our position is negative 2 meters. At 2 seconds, our position is negative 1 meter. At 3 seconds, we're right next to the tree, our position is 0. And, give myself room, at 4 seconds, we are at a position of 1 meter to the right of the tree. And you can see we can start to make this graph. And for a situation like this, where we have a constant velocity, a velocity that doesn't change, our graph is just going to be a straight line with a constant slope. To recap, we've defined a few quantities that are useful for describing motion. The first of which was position, which we called x. That's just where I was at different times. And I can actually say x depends on time. My position depends on what time you look at me. So we can write x as a function of time. Sometimes you will see x written this way, with parentheses and then a t. That does not mean that this is x times t. Sometimes you use parentheses to indicate multiplication. This means x is a function of t, or to put it another way, x depends on t. Position depends on what time you look at it. To be somewhat concrete, if I use the square brackets, I'll try to keep those square brackets to denote when I'm looking at a function versus when I'm using parentheses to multiply two quantities. But that was the first quantity we were concerned with, was position. Where are we? We also had time, which we just called t. So I can measure the time, just use a stopwatch to measure how much time has passed. Now, since x is changing over time, I can have different values of x. So I could have, for this diagram, we would have my final time is 4. My initial time is 0. My final position is 1 meter away from the tree. My initial position is negative 3 meters away from the tree. So we can write down, there's a final time, which I'll call t sub f, and an initial time, which I'll call t sub I. The change in time, I'm just going to denote that by delta t. Delta, for most physics and chemistry situations, just means the change in some quantity. Similarly, I can look at my final position, which in this case again is just 1 meter away from the tree. I could also have an initial position. Again, in this case, it's just negative 3 meters. If I look at the change in those two quantities, x final minus x initial, we call that delta x. We use the symbol delta x to represent that. We actually give that quantity a name since it shows up in a lot. We call that the displacement. So you've been displaced, or my person has been displaced by a certain amount. So if I look here, I finish, my final position is 1. My initial position was -3, so I would take +1 meter, I should need to include my units in there, +1 meter minus -3 meters. So I have been displaced by +4 meters. I have moved, or my person has moved 4 meters to the right. The other important quantity we can measure or use to describe motion with is velocity. So velocity gets the symbol v. And velocity is defined by how far I have moved in a given amount of time. So I have moved, in this case, I have moved 4 meters. Delta x is 4 meters, that's my displacement, in 4 seconds. So we could say delta v is just delta x, my displacement, my change in position, divided by the change in time. Now, there's another nice way to represent that involves looking at my graph. So if I look here, I can see that my x has changed by a certain amount. I'll call that delta x. Furthermore, my time has changed by the same amount, by a certain amount. I'll call that delta t. Now, we have a name for this in physics. In fact, I can put a delta t down here just to make it more explicit. We have a name for how far you rise up divided by how far you run along. That's just called the rise over the run, which you also know as the slope of the graph. So your velocity is the slope of a position versus time graph. If I look at the slope, I can get the velocity from the graph. All right, let's test what you've learned by doing an example. So I have here a motion diagram. T equals 0 seconds, we're at 2 meters. 1 second, we're at 0 meters. 2 seconds, we're at -2. 3, we're at -4, etc., etc. Here's what I want you to do. See if you can plot a position versus time graph. Tell me, is the initial position positive or negative? Is the final position positive or negative? Is the displacement positive or negative? And is the velocity positive or negative? I'll give you a few minutes. You can pause the video. Let's see how you do. All right, let's see how you did. I want to make my graph. I'm going to make a position versus time graph, so that will be x versus time t. And I look here, I can see at 0 seconds, I am 2 meters away from the origin. So here's the origin. Let's call this 2 meters. Let's say x is in meters. Should always put units on my plots. X is in meters. My time is in seconds. Initially, I'm 2 meters from the origin. At x is 0 meters, x is 0 meters at 1 second. So 1 second later, we'll say this is 1 second. 1 second, I'm here. 2 seconds, I'm at -2 meters. So that would be down here. 3 seconds, I'm at -4 meters. So 1 second, 2 seconds, 3 seconds. 2 seconds, we're at -2 meters. 3 seconds, we're at -4 meters. So we can see we're getting a downward sloping line. Now, let's see if we can figure out what all my different quantities are. Is my initial position positive or negative? Well, my initial position is 2, so that would be positive. Is my final position positive or negative? My final position is I'm at negative 4 meters, so that would be negative. Is my displacement positive or negative? Well, I started at 2, and then I got more negative. I went down in x, so my displacement is going to be negative. How negative is it? Well, I went from 2 to minus 4. That means I've gone down by 6, which means my displacement has to be negative 6. So displacement is negative. What about my velocity? Well, we know velocity is equal to the displacement divided by the change in time. The displacement's negative, therefore the velocity should be negative. Let's see if we can figure out how negative it is. Well, let's see, I've been displaced by negative 6 meters. I've gone down by 6 meters. And that took 3 seconds. 3 seconds on my, have ticked off in the time that I've gone negative 6 meters. So that would be negative 6 meters divided by 3 seconds. 6 divided by 3 is 2, so that would be a velocity of negative 2 meters per second. Let's try another example. This time we're going to go in the opposite direction. We're going to start with a position versus time graph, and we're going to make a motion diagram. So let's say, first thing I want to do is set my number line. I'll call this the origin. Let's see, it looks like the largest I get is 6 meters. Here's x in meters. I'm going to give myself more room here so I can make that a bit neater. There we go. Let's say this is the largest I get, which is 6 meters. X is going to be in meters. Let's say that's 4 meters. Let's say that's 2 meters. Now I look up here. I start at x is 6 meters. So I'll say here you are. T equals 0 seconds. After 1 second, we're now at 4 meters. So 1 second. We're at 4 meters. 2 seconds, we're at 2 meters. T equals 2 seconds, we're at 2 meters. And at 3 seconds, we are at x equals 0. So at 3 seconds, we are at x equals 0. So that's my motion diagram. Let's see, is my initial position positive or negative? Well, initial position is plus 6 meters, so that's positive. What about my final position? My final position is 0, so that's neither positive nor negative. We would have to say that my final position is 0. Trick question. My displacement, is that positive or negative? Well, I've gone from 6 to 0, so that means my displacement has got to be negative. I'm going down in numbers, so my displacement is negative 6 meters, back from where I started. What about my velocity? Well, I can see here that my velocity is, my slope is negative. It's a downward sloping line, which tells me my velocity has to be negative. If I want to figure it out, again, we can take the rise over the run. So my rise is actually more of a fall because it's negative 6 meters over 3 seconds. should give me a velocity of -2 meters per second, just taking the -6 divided by the 3.